So today we are really honored to have Dr. Julius Seidel as our speaker. Dr. Seidel is a postdoctoral fellow at the European Southern Observatory, mainly working at ESO's Perennial Observatory as one of ESO's ESPRESSO instrument fellows. She has obtained her PhD at the University of Geneva in Switzerland on the study of exoplanet atmospheres. Her works focuses on the observation of atmospheric dynamics and the various applications of narrowband, high-resolution spectroscopy. She additionally works on the study of terrestrial atmospheric conditions at telescope sites and various outreach projects geared towards Latin America. And Julia, when you are ready, you can start sharing your screen and your slides.
All right. I think you have to stop sharing before I can.
Okay, sorry.
Yep, can everybody? Excellent. Thank you very much, Daniel, for the very, very kind introduction. So as you can see, this talk will be heavily flavored by the European Southern Observatory, where you can see an array of our telescopes here on my first introductory slide. So the technique that I use, the narrowband high resolution spectroscopy, to learn something about the atmospheres of exoplanets, can obviously be used with any high resolution spectrograph, preferably a stabilized one. So for example, a few of my colleagues are also working with high-res data from Keck. So all of this is very much transferable to other telescope sites. But let's jump right in. So I'm starting with a little bit of an overview and introduction. Then I introduce the very basic techniques so that we are all on the same page. I'll give you some recent results concerning my favorite topic, which is the dynamics, so the winds, the weather on exoplanets. And then I'll switch to something completely different and show that what I do and what narrowband high resolution spectroscopy can do in general can also be used for applications completely outside of the atmospheric field, where we can learn something about the magnetic fields of exoplanets, and we can even learn something about satellites and planetary companions. So I leave you my email and my Twitter here in case you want to reach out. All right, let's dive right into it. So planetary discoveries are by no means something new, although the field of exoplanets and especially exoplanet atmospheres still feels a little bit like the wild, wild west. So even before the conquering and the colonization of Latin America, the Inca already had an understanding of planets. They called them estrellas errantes, which means basically wandering stars, because they didn't have access to telescopes, but they were very much aware that there's 5 visible planets in our solar system that move apart from the stellar background, so to say. And they based many things on these moving stars. So harvest season was based on the movement. Venus and Mars especially were very important, so that you even weren't allowed to start war during times when one of the planets was invisible. So that had quite the important impact on their lives. And to the point even where they made the movement of these moving stars part of their calendar. And this isn't just to show you the cultural impact that planets have always had on our civilizations, but also this is the very start of what I would call the planetary or the exoplanetary sciences, because even all the way to the beginning of the 9th century, there were observatories solely dedicated to tracking the movement of these wandering stars through the sky. That were then marked on the walls of these tiny observatories to track when the harvest season should start or when certain things couldn't be done. So this is, I think, one of the first examples of observatory activity in the Americas. But we couldn't obviously leave it there. So if we now jump a solid 800 years forward, and we're at the beginning of the 1800s in Russia, one of our colleagues called Lomonosov actually observed the transit of Venus that happened during that 12-year time frame twice. And he not only observed the transit of Venus, so, you know, one more example of detecting Venus as a planet, but he actually observed the refraction of light in the atmosphere of Venus. So this is undoubtedly the first detection of an extraterrestrial atmosphere, you know, which you can see here in the paintings. And then Kamali et al. Redid this experiment to see that it was really possible in 2004 using the same means that they had in the 18th century, and took a picture of exactly what Lomonosov was able to see in the 1800s. So here we go, atmospheres were found. It took quite a while until we made the jump from detecting planets and atmospheres in our own solar system and kind of breached the barrier to the extrasolar exploration. So it took all the way to 1995 through a stint of pulsar planets and disk detections in the 70s, 80s, and 90s to finally get the first exoplanet candidate around solar type stars. That's something that we can somewhat understand a bit better. And for the 20th anniversary, NASA actually gave a very nice conference titled The Discovery That Changed the Way We See Our Universe, which was the detection of the ultra-hot Jupiter 51 PEG-b that is orbiting around one of our neighboring stars. And in good European fashion, the Swedish Academy gave 2 Swiss researchers the Nobel Prize for that discovery in 2019. I happened to be in Geneva at the time where both of these professors are located, and the party was very good. So that was just, let's say, the start of the race for more exoplanets. And it kind of was a little bit of a slow start. Every time you do something new, it takes a while to be replicated. So while exoplanets started to trickle in 1 or 2 or a candidate here and there during the late 90s, then I think the real change in our observation strategy came with the satellite missions. So you can really see the start of the Spitzer tests and other satellite missions with these jumps during the 2010s. And now, obviously, this has stopped 2 years ago, but I have to update this plot. And in the last 2 years, we have now breached the 5,000 mark. So we are really now in the realm where we can do population studies, and we will also have quite a bunch of very good candidates to do follow-up on. So we're now starting to leave the realm of exoplanet discoveries, and we're starting to be in the realm of exoplanet descriptions or exoplanet exploration in a more wider scale. So now that we are kind of have the historical background of what we're doing, let's get a little bit into the technical details. So there's 2 very important means of observations that I use primarily, or that the field uses primarily. And the first one, that is the more intuitive one, is transit photometry. And I like to introduce that with my favorite. I love comics. So I always think of transit photometry as the bat signal. So it works exactly the same way. We have a light source that can either be a flashlight of Captain Gordon on the tower of Gotham City Police Department, or it can be a star. And then we have a projection surface that can either be the very gray night sky, or it can also be a telescope. And then while the light travels from our source to our projection surface, so while we collect photons from a star, something photobombs us and makes a projection. And this is what happens during an exoplanet transit. So the planet occults part of the stellar disk. And from this occultation, because it is proportional to the size of the planetary disk to the stellar disk, we can learn something about the radius ratio between the star and the planet. And we can also learn something about the duration of the transit and therefore the orbit of this exoplanet. So this is already quite some information to have to characterize an exoplanet. But on top of this drop in visible light, this drop in photons that we collect with our telescopes during an exoplanet transit, a few very, very lucky photons not only get absorbed by our telescope after this very, very long, many light years journey. But they even got lucky enough to, on this way, cross through the atmosphere of the exoplanet, just like we saw during the Venus transit in the 1800s. So this tiny, tiny speck of light that kind of gets refracted around the planet is what I use in the so-called transit spectroscopy. Because what happens is that the light interacts with the particles that are in the atmosphere, and they do what they do in our atmosphere as well. The blue light gets scattered, the red light gets absorbed not as easily, and we have everything in between. So if we have an element in the atmosphere that is very good at absorbing light, then we will see that in this specific wavelength, the exoplanet will appear a little bit bigger just because the part of the atmosphere has become opaque. And this is what we use when we make a narrowband transmission spectra. We basically scan the visible light. You can also do this in the infrared in wavelength. And then depending on what element is in the atmosphere, how much light was absorbed, we get a larger absorption that translates to a larger visible planetary radius or a smaller one. And this is something you'll see throughout the seminar. So this is the working horse of planetary characterization. You basically separate out the light that traveled through the atmosphere, and with these basically 3 photons, you try to learn something about what's happening in that very, very far away world. All right, so now that we have the theoretical tools, let's see what are our targets. So I mainly have worked so far on ultra-hot Jupiters, which are like our Jupiter gas giants, but they're just very close to the host star, which means they get blasted by irradiation, basically like a sandblaster for cleaning your house. And this is a 2-scale animation that ESA did of the WASP-76 system, which is the system that I'll talk about also extensively today. And it always blows my mind seeing this because this is really 2-scale. So the star and planet size are 2-scale, and so is the distance. So WASP-76b is only 0.03 AU from its host star, which means it's 3% of the distance from Earth to our sun. That means, first of all, WASP-76, the star, will look absolutely gigantic in the night sky. But it also means that the planet is tidally locked. So like our moon is always the same side that faces the star, which means that one side is always blasted by this absolutely gigantic amount of solar irradiation, and the other side always faces the universe and is therefore much colder. And if we now look at a diagram of the population of exoplanets found so far in the radius irradiation space, so we have planetary radius in Earth radii on the left, and we have on the horizontal the irradiation also in Earth amounts of irradiation. So Earth would sit at 1,1. So what you can directly see here is there is this blob of Jupiter-sized planets kind of above 11 planetary radii, Earth radii, I mean, that are highly irradiated. So from a few hundred times the irradiation that we receive on Earth up to about 10,000, and then we have the lovely outlier Cat 9b that is technically an ultra-hot Jupiter, but I more call it a burnt Jupiter because that's really far out there in terms of irradiation. So these hot Jupiters, and I highlight here WASP-121b, WASP-76b, and WASP-49b because those are the 3 that I'll mostly focus on today. They have a few characteristics that make them really interesting. So first of all, they're in chemical equilibrium, and because they are just so hot, molecules can't really hold their bonds together anymore. So the molecules are mostly dissociated into atoms, at least on the day side, so on the hot side of the planet. We have barely any hazes or clouds, which makes the atmospheres very observable. And this really makes ultra-hot Jupiters, so the ones on the hotter side of the spectrum, the benchmark cases for hot Jupiters, and that makes them the benchmark case for all exploration of exoplanet atmospheres, simply because if our techniques if a technique doesn't work on ultra-hot Jupiters, your hope of having it work on smaller and cooler planets is even less likely. So now that you know which planets we're going to talk about, let's dive into the scientific results. And first, I'm going to talk about atmospheric dynamics, because that's my favorite. And then I'm going to also talk a little bit about what secondary applications atmospheric dynamic studies can have. And just as a caveat, so atmospheric dynamics here, I'm talking about what can we say about atmospheric dynamics from an observational point of view. So what can we really learn from the data quality at this point in time? And this has very little to do with the theoretical realm, global circulation models and such, that can really give us from first principles an understanding how does the dynamics of these atmosphere work. So this is kind of not a bottom to top approach, but a top to bottom approach. And I feel like this is best illustrated with an example. So here we have a hot Jupiter, HD 189733b, one of our favorites. And for the field of exoplanet atmospheres really in ancient times, so 7 years ago in 2015, a paper was published by Aurélien Wittenbach, and they used HARPS data that was taken 2-3 years prior with the HARPS spectrograph, that is also a high resolution narrowband spectrograph installed at a 3.6 meter telescope in La Silla Observatory here in Chile. And to everybody's surprise, they found neutral sodium lines. So they found the sodium doublet, which is a resonant doublet and therefore very easily observable, but they found neutral sodium. And what they did is what I sometimes like to call the Frankenstein model. So they used the ETA code, Exoplanet Transit Atmospheres code, that basically tries to fit the broadening of transmission spectral lines just by using temperature and pressure broadening in a very, very basic one-dimensional model. So this worked actually quite beautifully, as you can see here with the color scale. So in kind of the continuum, so where the atmosphere starts to be opaque, they get a temperature of 1500 kelvins, and then the higher you go up, the higher goes the temperature. So this is a one-dimensional model. You basically hack up the data, you fit different temperatures to it, and that's it. But even already in 2015, they realized this is great. This is already very cool science, but there seems to be some physics missing. So a lot of the broadening that we see observationally in the lines can't be explained only by the pressure and the temperature of the atmosphere. So it seems that there's some other mechanism for broadening that it's missing. And the idea that we then proposed was, well, there's a lot of other things happening in atmospheres. So we don't really know where the continuum sits. It's just where the atmosphere starts to be opaque, basically, in the continuum from Rayleigh scattering or Mie scattering or H- interactions. But this is degenerate with the abundance of sodium. So maybe this is something that plays a role. And then there's also atmospheric dynamics. So we all know the Doppler effect, the same with an ambulance, that when it comes towards you, it's a higher pitch, and then it decreases in pitch as it moves away because the wavelength of the sound changes. And this can also happen to light. So if the particles that absorb the light in the atmosphere are moved by very strong winds, then the absorption position of the light and wavelength is kind of shifted by a certain degree because of this Doppler effect. But as you can see already, now we're starting to have a parameter space and not just a one parameter model. And that means that there are various degeneracies, and it's very hard to just make a grid and explore this entire parameter space, especially when you have, I now highlighted 3 parameters, but there's much more to it than that. So my work in 2019 and in early 2020 was to combine this one-dimensional model, kind of spruce it up a bit and make it 3-dimensional. So I created a 3-dimensional code for the atmosphere. I said, okay, let's try for different wind patterns that we know exist in our solar system and take, for example, Jupiter as an example. And then to save us the hassle of calculating thousands of models, because a PhD is only 4 years in Switzerland, I combined this with a multi-nested sampling retrieval to explore the entire parameter space. And this is called the MERC model, which is a self-contained code where you feed any sort of line, basically, for now the sodium doublet, and then it tells you what kind of atmospheric conditions are most likely to create the line shape of these lines. So this was pretty much theory. It wasn't really clear if that would work or not. So first I tried my hand at a two-dimensional model to make things a little bit easier, and I tried to apply it to the very same data that you just saw in 2020. And surprisingly enough, that worked really well, actually. So here you see two models, and Merck said very clearly, I prefer one over all of the others. So this is basically the base model that they tried in the Wittenbach et al. Paper, which you see in blue. And that's already not a bad fit to the lines, especially to the bind data that you see kind of the thicker lines, but it's clear that there's some sort of physics missing. So just the temperature broadening without any atmospheric dynamics is okay, but it's also not doing a very good job. It gets much better if you then include an outwards blowing kind of upwards streaming wind that is not entirely unexpected from a planet that receives a lot of irradiations. It's kind of puffing the planet atmosphere up. And that creates a much broader line shape and is very much preferred in the Bayesian evidence framework over a model without wind. So that was a real success. Although planetary rotation wasn't accounted for, and it was only a two-dimensional model, so there were a lot of details of winds and of atmospheres that weren't accounted for. So all of the wind speeds that I provided in the paper are really just very, very upper limits. It's more about the wind pattern that were retrieved and not so much about the wind speed. So I moved on to the ultra-hot Jupiter WASP-76b that you saw in one of the earlier plots that I showed. And to everybody's surprise, there is also neutral sodium in an ultra-hot Jupiter. The atmosphere is over 2000 kelvins hot, and still the recombination rate of sodium seems to be fast enough to offset the ionization, and we still have a little bit of neutral sodium in the upper realms of the atmosphere, which is really, really surprising because sodium really shouldn't, in these high layers of the atmosphere, should be ionized. The irradiation should be just too strong. But so we found it again with HARPS data collected at the 3.6 meter telescope. And that was the first sodium detection for an ultra-hot Jupiter. And the absolute absorption was quite large. We detected it at a 10 sigma level. And again, the sodium doublet, which was much broader, much larger than we had anticipated, very much like HD 1897333b. This is highlighted again here, where you can see both sodium lines combined in velocity space and now flipped from an absorption to the height in the exoplanet atmospheres. You can see that, okay, the sodium is really accelerated fast in velocity space. It's nearly at the escape velocity, and it's much, much broader than the minimum line broadening that the HARPS instrument can detect, which is marked here in yellow. But we all know science is only as good as it is reproducible. So years later, Tabernero et al. In 2020 used WASP-76 data obtained with the updated ESPRESSO spectrograph at the very large telescopes here at the Paranal Observatory of ESO. And for two different transits, so you see in the top panel transit number 1 and in the bottom panel transit number 2, you again find this very broad, very large sodium doublet for WASP-76. Different group, different technique, different pipeline, different instrument, different time 2 years later, and still it's there. So that kind of makes this quite robust. And also the VLT has an 8 meter mirror compared to a 3.6 meter mirror where HARPS is installed. So the precision of these two data sets is really just outstanding. So that obviously tickled my imagination immediately. And I combined the 3 nights that we analyzed and obtained with HARPS with the 2 nights that were obtained in Tabernero et al. And I created an extremely precise sodium doublet. Like, I think this is the prettiest data set I've seen in a long time. And I updated the MERC code to now be actually really quasi three-dimensional, including the rotation of the planet, which accounts for a little bit of rotational broadening because the atmosphere rotates with the planet, and to also allow for different wind patterns in different layers of altitude, meaning that not only could I try out different wind patterns that we find in Jupiter, but I could also vary them with altitude and with longitude, so that I have stronger wind speeds at the equator as is expected, and that we have no or a very slow wind at the poles. So, and what you can see here is, first of all, that the line shape itself, just from the data points, is kind of wonky. So there is a little bit of a slope on one side of the sodium doublet that isn't really seen on the other. And the interesting thing is that this can be reproduced using the Merck code by saying, okay, we still see in the upper atmosphere this outwards blowing wind that kind of pulls the neutral sodium from the lower atmosphere upwards fast enough so that we can still see it before it ionizes, but also that in the lower atmosphere, and with lower I mean everything below 10 to the -3 bar, so not really that low actually, there is a day to night side wind, so transporting particles from this always irradiated hot side of the atmosphere to the side that faces the universe, where it's always much colder. So that sodium is kind of dragged from this hot to this cool side and in a circulatory motion in the lower atmosphere. And the wind speeds that are now quite a lot more accurate because rotation and more physical wind patterns are accounted for, said that, okay, in the upper atmosphere, the wind speed is really quite gigantic at 20 kilometers per second. This again is probably an upper limit because the sodium abundance isn't varied in altitude. So there is a little bit of a caveat here. But for the lower atmosphere, we get a wind speed transporting sodium across the terminator with around 5.5 kilometers per second. And this is quite interesting because so this was published in 2021. And a few months earlier, Ehrenreich et al. Used the same data set, but using a different element. So they looked at iron. Iron is much heavier. So iron is mostly found in the lower atmospheres of exoplanets. And because the data is so good, they were able to trace iron using the cross-correlation technique in time. So they took all of the different small iron lines, combined it with the cross-correlation technique. And you can see here the radial velocity in the planetary rest frame on the y-axis, the concentration of sodium as the color or grayscale, so that lighter colors correspond to more iron. And on the vertical axis, you have the time, so that we kind of start the transit as the lower dashed line, and then we continue through the transit until we reach the top dashed line. And what you would expect normally is that it looks kind of something like this. You know, iron is present, but it's present at a certain offset in the planetary rest frame. And this means we have homogeneous iron in the lower atmosphere. We detected iron and everybody's very happy. But what they actually found is more like this. So that iron kind of seems to start at rest at 0 velocity, and then it starts to move towards 10 kilometers per second offset and remains there until the exit of the transit. And so David Ehrenreich provided kind of a toy model what that could mean for the atmosphere, which was later theoretically reproduced with global circulation models by Wardenier et al., which I also highly recommend you to read. Very good paper. And what they kind of say is, okay, if this is kind of what we see. So we as the observers, we're the eye on the right side, we have the star on the left side, and this is what we see in transit. So we just look at it from the top, we have the polar view of the planet. Then we have the leading limb, the part of the atmosphere that moves over the stellar surface first. And then we have kind of the trailing limb with the direction of motion indicated here. And now if we add rotation to it, then we have this morning terminator, so the one that's first to enter the transit, and then the evening terminator. And just because was 76b is tardily locked, that leads already to kind of a rotation of +5 kilometers per second in Doppler shift for the leading limb and -5 kilometers per second for the trailing limb, which would mean that we would see iron if it were at rest or just moving with the atmosphere at a continuous track starting at -5 kilometers per second to +5 kilometers per second. But we don't see that. We start at 0 and then we move to 10 and we stay there. Kind of weird. So the idea is, okay, if the iron gets heated up while it's on the day side, but the atmosphere is also rotating, this hottest point where the iron abundance is the highest, it's kind of a little bit offset towards the trailing limb because the iron needs a little bit more time to be heated up and is then kind of dragged with the atmosphere. And if to that, we now add a day to night side wind of 5 kilometers, so that this iron is kind of dragged simply by this day to night side wind in the atmosphere over both limbs from this hottest point, that would mean that for the trailing limb, we have the rotation of the planet itself, plus the atmospheric dynamics of 5 kilometers per second, leading us to an offset of 10 kilometers per second. And on the leading limb, the day to night side wind is offset by the planetary rotation itself. So iron, although it is moving within the planet atmosphere, to us appears at 0 kilometers an hour. And that is exactly what is observational seen here. So that we start at 0 when the leading limb comes into view. And then when the trailing limb joins us, we see iron at this 10 kilometer per second offset. And if you remember what I showed you from my very independent analysis on a completely different element with a completely different technique, then you realize, hey, Julia also found this 5 kilometer per second day to night side wind in the lower atmosphere. So two observational methods give us the same estimate for wind speeds in this atmosphere, which I think is very exciting when you think about using these wind estimates then as benchmarks for theoretical models. And that was quite a popular paper that David Ehrenreich published there. And the conclusion was that it's raining iron on WASP 76b because the iron is moved from the hot side to the cold side. And at the terminator, so when it kind of switches from the hot to the cool side, it will condensate, creating something quite similar to rain. All right, so now I want to give you a little bit of a perspective where we plan on going with the study of atmospheric dynamics. Then I'm going to switch to something completely different, and I hope you're going to enjoy it anyway. So as a perspective, for now, I talk mostly about hot and ultra Jupiters that are in the realm that I marked here as orange. But obviously, we want to push this a little bit further. So the idea is, what can we do maybe not for cooler planets just yet, but what can we do at least for smaller planets? Like, can we push this into what we call the Neptune Desert? So this realm where like hot planets the size of Neptune should exist, but somehow by photoevaporation or by other means, they just lose their atmosphere because their gravitation isn't strong enough to keep the atmosphere bound from the continued sand or light blasting by their host star. And one of these very interesting worlds that is kind of already in the Neptune Desert, but still has an atmosphere, is WASP 166b. So I recently had a look at WASP 166b. In 2020, I already studied this planet with HARPS, and now we looked at it again with ESPRESSO, and again we found sodium, which is interesting because it means that WASP 76b has an atmosphere, it has sodium, and we can, when we get a little bit more data, start to study its atmospheric dynamics and learn something about what makes the Neptune Desert really tick. Like, why do some planets that are in the Neptune Desert get to keep their atmospheres? And I'm kind of hinting at something that I'm going to talk about a little bit later, but I think a vast majority of these strange worlds that have atmospheres and have particles that they're not supposed to have actually come from. So this study is really exciting, but obviously I'd like to push this to cooler planets where the lines of neutral atoms are more rare and smaller, and also to smaller planets that are equally highly irradiated. So I'm personally very excited for the TMT, wherever it might be built, and also for the ND spectrograph at the ELT. And just to show you a little bit that it sounds really far away, but it's actually happening probably within the next 5 years, or let's be a little bit more conservative, the next 10 years. I think until 2030, we're going to be there. So this is from February. This is a picture of the ELT construction site just next door to us here. So you can see where I'm staying, where I'm right now in the background. This white blob in the very far background is where I'm right now and give this presentation to you. And that was in February. So right now, this kind of start of the dome that you see on the left has extended all around the ring. And the base work for the ELT here is really making a lot of progress. I'm very excited for that. Okay, and now to something completely different. So you've heard 25 minutes about winds, very exciting. But what else is this good for? I mean, winds are fun, but science is best when it has more than one application. So very, very recently, I actually learned about this. So there's I actually call it a new branch of exoplanet atmospheric physics that tries to understand more about its magnetic fields, which is a notoriously hard job and a notoriously underfunded and overlooked job, because we know that nobody likes magnetic fields. Everybody blames everything on magnetic fields, and nobody knows how to study them because they're not really observable. So I particularly enjoyed this paper that came out just a few weeks ago by Knirem et al., where they made models to understand, okay, what happens for exoplanets that have neither very strong magnetic fields or have very low ionization rates, kind of in the realm of like ohmic dissipation probably being the driver of magnetic fields. So they provided this model that you see in light blue here, kind of in the central part of the plot, where they plotted the equilibrium temperature of the exoplanet versus the maximum wind speed of the jets in the lower atmosphere that would interact with a magnetic field. And this is kind of interesting because I have never heard of this. I only found out about this because they used the results from my paper as input for their paper. So you can see here the data point for WASP 76, and from Cawley et al. The data point for WASP 33b that they used to kind of benchmark their model for the strong magnetic fields, and then provide another explanation for HD 209458b that kind of sits much lower in the thermal equilibrium range, and therefore also in a different magnetic realm in theory. So I'm kind of excited about this because very soon there's a paper coming out by Danny Mounzer that I encourage you to read, that is currently under review. And I'm not going to tell you which planet this is, so don't go looking for it. But I can already tell you that the wind speed that I retrieved for Danny in his paper sits exactly smack where their model is. So ohmic dissipation seems to be a really good candidate to explain this intermediate range of magnetic fields. So this is one application that I find personally very exciting, because magnetic fields is something that we barely understand and all of our models desperately need to include. So I think this is very, very important. And the second part that I found surprising and that I did not consider a possibility to come out of this is the question of satellites and companions to exoplanets. So there's a very large, very successful community looking for moons and satellites of all sorts in light curves. So for example, the group of David Kipping or also Alex Tichy, currently in Taiwan, they're very good at this, and recently published a Nature paper on a moon candidate that I found very fascinating. But we can also kind of supplement this light curve work using the atmospheric signals themselves. So this is a little video taken in 1991, 30 years ago, by Schneider et al. And this isn't an exoplanet, unfortunately. This is Jupiter and its moon Io. And what you see here is a video taken in the yellow wavelength of the visible light, and you can see sodium. So this is this comet-like tail where you can see that elements are kind of explosively outgassing from Io and accreting on towards Jupiter. That is pure sodium, which led my colleague Oza to believe maybe for some of these planets where we see sodium, the sodium doesn't actually come from the planet itself, where it should be ionized, if not protected by a magnetic field. But maybe this sodium comes from some form of debris disk or cloud that travels with the planet from a destroyed or in the process of being destroyed satellite or moon. So this is what they tried for WASP-121, where 3 nights of HARPS data were combined, and Jens Heumeckes, who led this study in 2020, has the approach of let 1,000 models bloom. So he invited everybody who tries to do atmospheric modeling on data, so data-driven modeling, and said, please try and tell me what I see. And it was very interesting that my model trying to explain what we see in sodium just from winds failed spectacularly. So I was like, winds? I mean, either the data set isn't super good yet because this is all still very noisy data, but winds don't really do a good job for this particular data set. And the PAWN model, which tries to explain what we see with solar-driven Parker winds, did a little bit of a better job, but still couldn't really grasp the line shape. The only model that was relatively successful in reproducing what we saw observationally speaking was if we say, okay, the sodium doesn't actually live in the planetary atmosphere. It inhabits an optically thin torus around the equator of the planet, probably from some form of disk structure or from some disintegrating satellite from Gebek and Oza 2020. And this is also super interesting, and they dove a little bit deeper in this in Gebek and Oza, where they showed that really the hydrostatic model, and even if you really crank up the sodium abundance, doesn't do nearly as good a job as if you postulate what they call an exo-Io, so an Io-type moon around an exoplanet. So this is super interesting. And right now I'm going to show you a little bit of things that aren't published yet. So if it's possible, Daniela, I didn't say that, but if you could stop the recording for a few minutes, that would be great. But if not, that's also totally fine.
Oh yeah, in the recording that I'll put online, I'll probably just
excellent
like censor
right.
this parts.
Yes, that's lovely. So because we have submitted it, but it's not published yet, and we'll see where it goes. So just that all together, we kind of have an understanding what we're looking for. So you saw at the very start what light curves look like. So you have this dip when the planet comes in view on the stellar disk. And if you do that in relative absorption, so you kind of forget about the planet, and you just say, okay, if I just look at sodium that hopefully comes from the planet, and I try to track the sodium signature in time, what's kind of the relative extra absorption that I just get from sodium? And this is, I didn't put this here, but this is from Seidel et al. 2019, where I did this exercise for WASP-76b, and this is what it's supposed to look like. So in green, you have out of transit, where you shouldn't have any planetary sodium absorption. And then in white is when we're in transit. And you can see that although scattered because the data quality is not super good, you can see there's some form of absorption happening. And then once you hit the green, there's nothing happening. And if you combine these 3 plus on the top, you get the lower relative light curve where you can really see, okay, while I'm in transit, there is definitely sodium being absorbed by something, most likely the atmosphere. And when I'm not in transit, there's nothing happening. And now comes the kicker. So Oza decided, let's do that and reanalyze the data for WASP-49b, where he suspected there's some form of satellite or debris disk that might come with the exoplanet. And in 2017, this data was published in Wittenbach et al. 2017, where they showed an absolutely gigantic sodium signature. But it being 2017, we were still mostly occupied by simply detecting new elements and weren't yet there thinking about where these might come from or what we can additionally learn from them. It was really just the start of the exoplanet atmospheric exploration. So we realized the data set and we found that out of the 3 nights, only one of them has actually sodium in there and the others were just flat. Even the ESPRESSO data with a much larger collecting power that OZO obtained about a year ago didn't show anything. So what we found is that the detection previously published stems basically from a 40-minute window where we have an absolutely gigantic sodium signature and then nothing. So what you see in this plot, and I try to break it down because it's relatively complicated, on the x-axis you have time with the yellow part showing the ingress of the Hill sphere, and then the green part showing the real transit time. And on the y-axis, you have the absorption. So how much extra relative sodium is there? And in the black dotted line, you see what we should see if it were similar to WASP 76. So we should see kind of this drop during the transit and then nothing while we're out of transit. But what we actually see is that during the transit, there seems to be no sodium absorption whatsoever happening coming from the atmosphere. But with the start of the ingress of the Hill sphere, there is this 40-minute window of an incredibly strong absorption at about 3 extra % just coming from the atmosphere. And using OZO's models of a thin torus around the planet or a moon, he comes to the conclusion that this is most likely an Enceladus style, so different type of moon, but still a very volcanic active type of moon that is orbiting WASP 49b, so WASP 49bi. We submitted that quite recently to Nature, and we haven't gotten news back yet, so I don't want to jinx it. And again, results are only as good as if they are reproducible. So we asked Aurora Caselli, who is now permanent staff at Caltech, if she could please look in cross correlation, so with a different technique, if she can find sodium. So maybe if we do our analysis incorrectly. But she sees the same thing. So you see one of the HARPS nights where there was no sodium found by us in the relative absorption light curve. And then you see the night where we see sodium supposedly coming from some sort of satellite or debris disk. And she says, guys, I see exactly the same thing. On the left, I see barely any sodium. It's kind of smeared out. There's not really anything to see. And then on the right side, I can really trace the sodium. It comes only from the very start of the transit. So as we see, the first 40 minutes basically, and is vastly offset from where I would expect sodium at the center of the black dashed lines. So this is where sodium should be if it were in the atmosphere of the exoplanet. I see it kind of offset to the edge of the Hill sphere. So this is super exciting. And I think this makes it a really important candidate to like study further to see like if this is maybe the first smaller moon that we can find with a technique that is not studying the light curves. So hopefully this will be published sometime later this year. Let's see if it's Nature or if it's a different journal. So in summary, there's really just lots that we don't know about exoplanet atmospheres. They're very elusive with 3 photons that they send us every now and then. And I think the takeaway is if we really don't understand our techniques when we use them on ultra-hot Jupiters, we won't understand hot Jupiters and we won't understand smaller, cooler planets. And that we can learn something about winds from resolved spectral lines. We know now that in ultra-hot Jupiters, at least, the upper atmosphere shows very strong outwards pushing wind that kind of propels even neutral atoms outwards. That's maybe driven by magnetic fields. This is a line of investigation I'm still following. And that in the lower atmosphere, we have these day to night side winds that transport material from the hot side to the cooler side. And this is something that we can also study now that we have these ultra high resolution spectrographs at very large telescopes by time resolving these signatures. So instead of, as we did before, integrating over the entire transit, we have now started at least to be able to do time resolved detections. And of course, that wind studies are super important. Atmospheric dynamics are very important for three things. First of all, they give input to the theoretical models trying to understand atmospheric dynamics. So they give kind of a observational framework to global circulation models. They can teach us something about indirectly about magnetic fields that we cannot otherwise observe. And they have to be employed to rule out false positive detections for for planetary companions, be it disks or debris fields or real moons, simply because if a moon can be explained just by atmospheric wind, it is not a good moon follow-up candidate. So in summary, really expect the unexpected for exoplanet atmospheres. Thank you so much for listening.